One thing to note is that it says as usual here. I'm not sure if we saw this in the previous lectures, but we can actually destruct these ands right when we introduce them. So by using this bracket pattern matching syntax here, it's going to intros n and m, and the brackets mean intros this as h, and then immediately call destruct as using these two names. Yeah. Can we invert the prop instead of destructing? Sorry, the question was, can we invert the assumption instead of destructing? And the answer is yes, it works in this case. Yes, that's all I'll say about that. Okay, so. Right, so you might have noticed that this idea, why would we ever end up with ands in the, why would we ever end up with an assumption that has this and form, right? Because as we saw, this is isomorphic to just making two assumptions, right? We can just assume n equals 0 and m equals 0. So why would we ever end up with a goal state that looks like this? Well, for the present example, both things work, but sometimes when you're working on a goal, you might want to assert some intermediate proposition or statement and prove it and then use it. So as an example, let's here we go. So as an example here, when we're trying to prove this goal, we're trying to show that n times m equals 0, assuming that n plus m equals 0. The natural way to prove this is to first show that n equals 0 and m equals 0. And we can do that by asserting this intermediate goal. We saw this tactic a little bit earlier. Now we have to prove this goal, which follows straightforwardly from some other sublemma that we've used previously. And after we prove it, we have this assumption in hand, but now we have an and we need some way of working with it. So we'll use destruct and proceed as before. There are other cases where and will crop up in an assumption, and we'll see one of those actually a little bit later in this lecture. Okay, and just as an aside, this little wedge operator is actually syntactic sugar for so A and AB, in much the same way as the equality symbol is actually syntactic sugar for this an EQ identifier. So what is the type of and? Well, if we check it, it's going to take a prop and another prop representing the two sides, and it's going to give us a new prop. Okay, so that's and. Just to recap, if we have an and in the goal, we can use split, and we'll get two new sub-goals. If we have an and in the assumption, we can use destruct, and we'll get two new assumptions. Okay, we have and. Yes?
And some sort of inductive type then, because we're using destruct, or is it just a coincidence that we're using destruct here?
So the question was, is and a inductive type because we're using destruct just as we did with other inductive types, or is it some weird coincidence? And the answer is, it is no coincidence. They are an inductive type, and we'll look at that definition in more detail tomorrow morning. Okay. Any other questions? Good. Okay, so we have ands. You have ands. What's the complement of and? It's or. As you probably remember from your Boolean logic class or when you did your circuit design. So in Coq, of course, we have conjunction for taking the disjunction of two propositions, which is right A or B, as we see here. The definition. Wow, I'll go aside. So okay, how do we prove statements that have an or in them? How do we work with goals that have or in them? So. Oh wait, are we going to use, okay, we're going to look at hypotheses first. Okay, so here's our or example. So what do we do if we have an assumption that is of the form A or B? So here's an example. We know either n equals 0 or m equals 0, and we want to show that n times m equals 0. So if you were doing this by hand, how would you go about proving this? Like, what would you do? you would do a case analysis on that OR, right? So you knew either n equals 0 or m equals 0, and that's precisely what we're going to do here. So here we have this, we're going to use this special intro syntax, and it's going to produce two sub-goals, one for where we get to assume that n equals 0, and one where we get to assume that m equals 0. In the case that n equals 0, we can rewrite with that and use reflexivity. Similarly, if m equals 0, we'll do the same thing. The idea here is that whereas if we had an assumption about and, we get one resulting sub-goal when we do case analysis on it, right? We get to assume both of the facts. Here, when we're doing case analysis on disjunction, we don't get both of the facts because there are two ways, effectively, we could have built up this proposition A or B. We could have built it up with A or we could have built it up with B. And so in order to prove that this holds under both cases, we have to show that it holds for both cases, right? Right, so this case analysis pattern HN or HM allows us to name the hypotheses that are generated, and that's why we have nice handles so that we can use when we do the rewriting. You could imagine that we could have done an intros of H and then destructed it, and we would have ended up in a similar proof state with two proof obligations. Okay, so that's what you do when you have an OR as an assumption. What do we need to do when we have an OR in the goal? How do we prove something of the type A or B? Okay, well, this is a little bit more pleasant than when we have an assumption, right? So if we want to show A or B, what do we need to show? A or B, right? It seems a little counterintuitively, but if we write down that as a proposition or a statement or a theorem in Coq or a lemma in Coq, it makes a little bit more sense, right? So what is this saying? This says, this OR intro, the statement of this OR intro lemma says, for any propositions, if you give me an A, I can give you A or B, right? And so what do we do here? We intros these assumptions, and now we have tactics for working with goals of the form, the goals that have disjunctions. So there's a left tactic, and what this says is, I will prove the left-hand side of this disjunction. So once we apply left, we have a new goal of type that says I need to prove A. Conveniently, we have that assumption, H of A. So we can just apply that directly, and we're done. If you can imagine a similar proof where you get to assume B, can you imagine what the tactic might be that you would use there? Right. Exactly right, yeah. Here's an example of a case where we might need to use both left and right in conjunction or with each other, disjunction with each other. Okay. So here, let me get this more in the middle of the screen here. We're going to do case analysis on n, this natural number. Here we need to show either that 0 equals 0 or 0 equals successor of something, well, predecessor of 0. Obviously, we're going to want to prove the left-hand side because that's easier. We'll call left. We'll get the left sub-goal. We'll solve that using reflexivity. In the other case, we're going to want to prove the right-hand side of the right disjunct. Here, well, we just need to show this equality, which is trivially true by simplification. We can call reflexivity on it, and we're done. It's worth re-emphasizing here. You probably noticed this when you're working through your homework, but you can imagine that reflexivity implicitly calls simple before it gets run. So you don't actually have to simplify a goal before calling reflexivity. And that's why I didn't need to simple away that predecessor of successor expression. Okay, so we have ands, we have ors. Another interesting logical operator is not, right? So what's interesting about not is so far we've exclusively proved things that are true, right? We've proved that 1 equals 1 or 1 plus 2 equals 2 plus 1, right? But sometimes you want to prove things aren't true, right? So we might want to prove that 1 is not equal to true, or 1 is not equal to 2. In Coq, of course, we're going to use the logical negation operator, which is not right here. Now, it's worthwhile to see how this not operator is actually defined. So we saw previously in the last lecture this idea that if you assume that we have this principle of explosion, the idea is if you have some contradictory assumption, everything follows from it, right? If you assume something that's false, you can immediately prove whatever you want, right? So you could exploit this intuition, right, and say, if we want to show that not P holds, right, all we would need to do is show that for any proposition, if we assume P, then that Q or assertion holds by default, right? This actually makes sense, but Coq is going to do something a little bit different. The idea here is we're going to define not P as P implies false, where false is this special contradictory proposition that's defined in the standard library. If you stop and squint, you could see this is equivalent to the other definition, right? Or certainly the first definition follows.
All right, so. Took all the batteries I could, so should be enough.
It should be enough.
Yes, like 12 batteries. Well,
Thank you. Thank you very much.
Intentional type theory. So the idea here is every expression you write in Koch intrinsically, intuitively, intrinsically has